Okay, good afternoon, everyone. This is the first talk in this room. I'm happy to introduce Professor Song Sen from Zhejiang University and also University of California, Berkeley. And his title is Kahler-Einstein matrix. Let's welcome.
Thank you, Professor Young, for the introduction. Thank the organizers for inviting me to give the talk and give me the opportunity to present this work. So we will talk about this paper, which is about a decade ago. So we will also discuss some further developments on related topics. So I've prepared a long file, so I expect I will not finish all of them. But in the meantime, please feel free to ask questions so that I got excuse not finish them on time. So 3 parts: background, main result, and further developments. So Kahler geometry studies triples Riemannian metric G, almost complex structure J, two form omega. They satisfy the algebraic condition and differential conditions. So the algebraic condition is a compatibility, pointwise compatibility between omega G and J. So any two of them determine the third. And the differential condition on omega and J, so they're integrable in the sense that the omega is closed, the omega is symbolic form, and the Nyinghaus tensor is 0, so J defines a complex structure, integrable. So a central theme in Kahler geometry is the connection between differential geometry, which deals with the metric mostly, and also you can think of the symbolic form if the complex structure is fixed, and a complex algebraic geometry, that's just the complex structure J. So there are two ways of entering Kahler geometry. So a common textbook is you start with a complex manifold, and then you choose local holomorphic coordinates, z1 up to zn. A Kahler form is a two form that's written in this way. So H alpha beta bar, this is a positive definite Hermitian matrix depending on the point. So it's essentially equivalent to the information of a Hermitian metric. It's just use this matrix. And the crucial condition is that d omega equals 0. And then some important fact is that given this condition, then omega is actually determined locally by a single function. So phi, and so it's d bar of phi. So phi is a pluri subharmonic function. So this makes obvious connections to several complex variable theory. If X is compact, then of course globally you cannot write the omega as a exact form, but there's topological information as a cohomology class of omega, the Raman cohomology, and that up to that it's essentially your variation of a function. So it's omega plus a global defined function, d bar of global defined function. So if you start with a complex manifold, essentially you are dealing with functions. A standard example is CPN with the Fubini-Study metric, and then you can restrict to submanifolds, complex submanifolds in X. Then same formula will just descend to X. But you can also, if you don't like formulas, you can also conceptually say view Kahler geometry as a Riemannian metric with special property of its holonomy group. So if a Riemannian metric G is Kahler, if it has holonomy group contained in the unitary group. So holonomy is determined by, so there's a picture. So that you start with a point, you draw a loop based at the point. This orange line is viewed as a tangent space at the point. So you can parallel transport the tangent vector along the loop, and you may, so you start with V, you may end up with a different vector, so P gamma of V. So this P gamma will determine a orthogonal transformation of the tangent space. So if you connect all the space of all such P gamma for like piecewise smooth gamma, then you will get the holonomy group. So it's a Lie group in general. So in general, it's a subgroup of the orthogonal group. The Kahler means that it's a subgroup of the unitary group. It's because the complex structure viewed as a tensor is parallel with respect to the Levi-Civita connection of the Riemannian metric. Conversely, if you know that a Riemannian metric has a holonomy group in UN, then essentially you can get a unique complex structure. There are some special cases, but for example, when the metric is hyperkähler, but you can think of this note that is important for me. The complex structure is essentially determined by the metric. So that means if you know the information about the metric, then in principle you can recover the complex structure. For example, on the Riemann surface, if you give a Riemannian metric on the Riemann surface, the complex structure is if you give a Riemannian metric on a two-dimensional surface, orientable, then the complex structure is determined by the Hodge-Star operator. And then, so I talk about Kahler, then I have to explain Einstein metric. So this has to do with Ricci curvature. So for Riemannian metric G, the Ricci curvature tensor is some average of curvature components that has to do in local normal coordinates, geodesic normal coordinates. You can write this Ricci as Rij dxi dxj. Whereas the Rij appears in the second order Taylor expansion of the square root of the volume form. Sorry, the volume form, square root determinant. But if the matrix is Kahler, then this volume form is given by omega to the nth power. So that determines the Hermitian metric on the anti-canonical line bundle. And then there's a curvature of the Chen connection of that Hermitian metric. And so it has a nicer expression that you don't need the geodesic normal coordinate. You can work with a holomorphic coordinate, and the Ricci curvature has this local form, so minus I d bar of log determinant of this matrix. The definition of the Kahler form. So this log determinant is only locally defined, but globally. But then you immediately from here you see that the Ricci form is closed, so it determines the cohomology class, and by Chen value theory, it's actually the first Chen class of X. So I will talk about the various notions of canonical Kahler metrics on complex manifold. So Kahler-Einstein metric just means it's a Kahler metric that is Einstein. So the Ricci tensor is proportional to the Riemannian metric. Equivalent, the Ricci form is proportional to the Kahler form. So locally, the equation will, so if you locally write omega as d bar of a function phi, this equation takes the form of a complex Monge-Ampère type equation. The determinant of this matrix is e to the negative lambda phi plus a given function for f. Just from the equation, if you take the cohomology class, you see there's a necessary condition for the manifold to admit a Kahler-Einstein metric, namely that the cohomology class of Ricci is proportional to the cohomology class of a Kahler form. So the first Chen class is definite. It's proportional to a cohomology class of Kahler form. So the sign of the lambda is uniquely determined. So when we say C1 is positive, it means that's lambda can be taken to be positive. And this sign will be important in solving the equation. But more generally, if the first Chen is not definite, then you cannot require the Ricci form to be proportional to omega, but you can require the Ricci form to be harmonic. It's a cohomology class. I mean, it's a D star and it's 0. So Ricci form is always closed. So the second equation is automatic. And by Bianchi identity, so that's equivalent to saying the scalar curvature of omega is constant. That's the average of the Ricci curvature. And this constant is topological constant, so, right, as underlying S. So this we call omega a CSCK metric. Even more generally, the CSCK metrics, they are special cases of as class of metrics called extremal Kahler metrics introduced by Calabi. So these are defined as critical points of the functional. So you work in the cohomology class, the Kahler form space of Kahler forms in a fixed cohomology class. You take its remaining curvature tensor L2 norm, and you try to minimize this. So this is I think Calabi's original motivation was from. I mean, this is the analog of the Yang-Mills functional for Kahler metrics. So there's a well-known story. The Calabi conjecture, 1954. There's a Kahler-Einstein metric on a complex manifold X if and only if the first Chen class of X is definite. So it's proved by Professor Yao, 1976, in the case when C1 is 0 or C1 is negative. And also in the C1 negative is also proved by O'Bine independently. And so that when the first Chen class is 0, the corresponding metric has a vanishing Ricci curvature. That's called a Calabi-Yao metric in general. In both cases, the Kahler-Einstein metric, we know they exist, but also they're unique. They're unique up to the change of cohomology class. So they can be viewed as canonical metrics associated to the complex manifold X and possibly the cohomology class. So when first Chen class is positive, so in algebraic geometry X is called the Fano manifold. So this is the mysterious case. So for one, we know that the Kahler-Einstein metrics do not always exist. So there are obstructions to the existence. So back in 1957, the Matsushima theorem, we know that if a Fano manifold means Kahler-Einstein metric, then the automorphism group has to be reductive. Namely, it's a complexification of a compact group, and the compact group is given by the isometric group, holomorphic isometric group of the Kahler-Einstein metric. So this is the if you work with a on the Lie algebra level, this is essentially a Bochner formula, the Bochner type formula. And then in 1983, it's discovered by Professor Futaki that there is a Lie algebra caricature. So this is on the Lie algebra of automorphism group of X. That's a Lie algebra of holomorphic vector fields on X. So it's always defined, and then if there's a Kahler-Einstein metric, then this has to vanish. So we will not define it now, but we'll come back to this later. So immediately there are examples, explicit examples without Kahler-Einstein metric. So for example, if you blow up CP2 at a point, so the automorphism group of CP2 is just 3x3 matrices. And if you want, for this thing, you have to make some. It becomes so that's you correspond to a matrix at a fixed point. So that's upper triangular matrix. That's not reductive. And we know that if the Kahler-Einstein metric exists, then there is a uniqueness. So it's not literally unique because in this final case, again, this has to do with the automorphism group. So automorphism group if you pull back a Kahler-Einstein metric by the automorphism group, it is still a Kahler-Einstein metric. So you can expect, at best, expect this is unique up to the automorphism group. So this is proved by Bando Mabuchi. Unique. It's actually slightly stronger. If it's unique, it's actually up to the action of the complexification of the isometry group. So of course, by Matsushima theorem, it's the same as the automorphism group, but it does not depend on the Matsushima theorem. So, before we get into the main theorem and get into very technical parts, let me just use one slide to explain that there's a heuristic reason why we believe that not all Fano manifolds can admit Kahler-Einstein metrics. So if you consider the space of all, so you fix a differential manifold, if you consider the space of all Fano complex structures on X, so namely the complex structure such that the first class is positive, and denoted by K, the space of Kahler-Einstein matrix with positive Ricci curvature on X. So of course, if I give a Kahler-Einstein matrix, the underlying complex structure is a Fano, so there's a map from K to J, and then it respects the diffeomorphism group action. So you have a map from the K. This is a moduli space, it's really moduli space, modular isomorphism. So because we have uniqueness, so this map is injective. So if so we claim that phi should not be surjective. If phi was surjective, then because the Kahler-Einstein metric is we believe is canonical, then if it's injective and surjective map, then with some extra little continuity, you can say that this phi has to be a homeomorphism. But this is the first thing we know about complex geometry, that the space of complex structure is not a Hausdorff modular isomorphism. That's a jumping of complex structures phenomenon. But there's no jumping of remaining metrics. So one space is non-Hausdorff, the other space is Hausdorff. You don't expect them to be homeomorphism in general. So there's a caveat here. So this suggests. So that's something that has to be justified. But in any case, I think that this is easier to understand than the later technical parts. So the main result is that for Fano manifold, that means a Kahler-Einstein metric if and only X is K stable. So this K stability is an algebro-geometric notion that we will spend some time explain later. We will not give the precise definition, but just to explain the geometry behind it. The only if direction was known due to the work of Chen, Donaldson, Chen, and Berman, and many others. So essentially the theorem says that the solvability of this nonlinear PDE reduces to algebra-geometric problems. So it's an analog of the previous Donaldson-Woudenberg-Yau theorem that identifies the existence of Hermitian Yang-Mills connections on holomorphic bundles with stability. So this theorem proves a conjecture that goes back to Yau for Kahler-Einstein metrics, and more generally, so this is so-called Yau-Tian-Donaldson conjecture. So if you take a compact complex manifold and not necessarily C1 definite, so if you just take an ample line bundle over the manifold, then this generalization of Kahler-Einstein to CSCK metric, the existence of a CSCK metric is if and only for the K stability of this pair. This is a manifold together with a ample line bundle. So our result proves the conjecture when X is a Fano and the line bundle is anti-canonical. So in general, this conjecture is still not known. So now let's enter K stability. At the time when we proved the theorem, this K stability was not a well-known or popular topic in algebraic geometry. I think nowadays it has seen extensive studies in algebraic geometry. But if you look at algebraic geometry papers, then the definitions will sound very mysterious. So I think I will just explain the motivation instead of technical definitions. So so we consider the question is to look for a solution to the equation, and so it's better if we work on. So this is the case when X is not necessarily Fano, just a general Kahler manifold. We can put the problem into a variational framework, and that's actually the origin of this problem for CSK matrix. So you consider fixed scalar class a space of all functions phi, such that if you add a dd bar phi, it's another Kahler form. So this is this is a subspace of this C infinity X, and it's open and it's convex in the obvious topology. But there's a Riemannian metric formally you can define on this space. So if you take a point in the space, a tangent, because this space is open, the tangent vector just functions. You take two tangent vectors at this point. The inner product is defined using the L2 inner product with respect to the measure defined by this omega phi. So the volume measure of omega phi. So this result, Mabuchi, Samus, Donaldson, that this space, you can formally calculate the curvature tensor is a symmetric space with non-positive curvature. It should be viewed as GC mod G, for if G is a compact group. So there's a lot of formal picture associated with this. And then, so the Mabuchi defined a functional so that the constant scalar curvature metric becomes a critical point of this functional. That's the Mabuchi functional. So this Mabuchi functional is defined in terms of its derivative. The derivative is a one form. So the one form is easy to see. It's very naive looking. You take a delta phi, just a tangent vector. You just get a L2 inner product of delta phi with the equation that you want to solve, scalar curvature minus the average. So if this is 0, of course, the scalar curvature has to be constant. And the non-trivial thing is that this alpha is a closed one form, and the space is contractible, so you can actually define a function. This function is defined up to the addition of a constant. So just from definition, it's easy to see that critical points are CSK matrix, and then Mabuchi did this formal computation. You can define geodesics, and then this function is geodesically convex on the space of potentials. So this is an analog of I think it's motivated by the Donaldson function in the case of Hermitian Young-Mills connections. And then, so I'm trying to. So the Futaki invariant, of course, defined before Mabuchi function, but you can recover the Futaki invariant using Mabuchi function. Just this formally, as auto 0 is just identity component of the automorphism group acts naturally on H by pulling back the Kahler metric. And you can check it preserves the one form alpha. So so it gives any vector field. Holomorphic vector actually generates a vector field on this space, and the pairing of this one form with the vector field is a constant on the space potentials. So it's defined as an invariant. It's called Futaki invariant. I mean, this is just for me, it's just a convenient way of explaining. So and of course, if alpha. If you have a CSK, then you just evaluate at the point, CSK point, then alpha is 0, so its Futaki invariant has to be 0. This does not depend on the choice of the metric, right? So it's constant on the space. And then this becomes, you have a convex function on a space, and you want to look for its critical point. So it's a picture. So if you have a convex function in one dimension, then the left hand side, it has a critical point. If it has a critical point, then its slope at infinity along both. If you move towards infinity, the slope, the derivative at infinity has to be positive or non-negative. So there's a technical problem here. But on the right, there's no critical point, and the slope on the right at infinity is negative. So this on the left picture is called a stable case, and the right picture is called the non-stable case. So stable corresponds to the case when the critical point exists. Non-stable corresponding no critical points. So then formally, one expect the existence of a critical point if and only for this function has a positive slope at infinity along any geodesic ray. Of course, this is very formal. This space itself is quite incomplete. It's infinite dimensional. So even the existence of these rays is a problem. And then there's also, of course, the geodesic bounded sets in this space is not going to be compact. So there are a lot of problems with this. But later we will see that over the years, after then actually there is one can make precise of this. Anyway, but K stability is just algebraic. It's algebraic thing that out of this you just replace geodesic rays, which you don't know how to construct, by one parameter subgroups in the finite dimensional Lie group PGL. So the way you do this is you embed your manifold into a projective space, and then a one parameter subgroup of PGL will degenerate your manifold in the projective space, and that degeneration will induce a geodesic ray. That's known. But anyway, so you can directly work with the degeneration, and then you make sense of this slope. So that's the notion of K stability. K stability is an algebro-geometric notion. I think it's first defined analytically by Chen in 1997 for Fano manifolds, and it was generalized and made algebraically by Donaldson in 2002. It generalized the Hilbert-Mumford criterion for stability in geometric invariant theory. It involves two concepts: test configurations and again Fataki invariant. So this Fataki invariant is sometimes people call it Donaldson Fataki invariant. It's a generalization of the previous Fataki invariant. So a test configuration is just something you test with. So it's just what I said informally a minute ago. So you pick a projective embedding of X into CPN using sections of this powers of this line bundle, and then you pick one parameter subgroup in PGL. So then you can take a limit of this X in the sense of schemes. So it could be very singular. So if you write all the defining equations of X, you take the limits of the defining equations up to scaling, you will get this. Anyway, but then the point is that this is algebro-geometric procedure, and then the Fataki invariant is a number associated to this. It's defined in terms of some weights, whatever. You don't need to know this. But the point is that if the limit x0 is smooth, and because of this you are degenerating using this C star, so there's a C star action on x0, and there's a homomorphic vector field on x0. So it agrees with the original Fataki invariant for that homomorphic vector field on x0 if x0 is smooth. So in algebra geometry, there are a lot of reformulations of this Fataki invariant and generalizations in terms of intersection numbers and so on and so forth. This is if you open more recent algebra geometric papers, that's probably the way they define Fataki invariant. So and we say that a polarized manifold X and L is K stable. if the Fataki invariant is non-negative for all test configurations, and it's positive, and that's in trivial cases, it's just the algebraic analog of this formal slope at infinity being positive. And there are many variations of this notion on different levels of strength. Ideas in the proof. So yeah, just very briefly, the main strategy is via continuous deformation. You start with a chosen initial Kähler metric. You want to deform into Kähler-Einstein metric via prescribed process. If the deformation breaks down at some point, then we produce a test configuration with negative Fataki invariant. So then, so that means if the breaks down, then it's not stable. So if it's stable, then never breaks down. So you will end up with a Kähler-Einstein metric. So in our original proof, we consider Kähler-Einstein matrix with cone singularities along a smooth divisor D. And so we consider the family of equations. So this equation, if beta is this cone angle, if beta equals 1, so there's no second term. It's just the usual Kähler-Einstein equation. But then by decreasing beta, you move curvature to the divisor. So this cone metrics, they have a very positive curvature along the divisor. So that this coefficient mu beta becomes negative when beta is very small. And we know that for negative Kähler-Einstein, we can apply the technique of Yau and our bind to solve the equation. So we start with beta very small, then mu beta is negative. We can solve the equation, and then Donaldson proved that this you have openness. You can always increase beta a little, and then the point is we need to increase beta until beta equals 1. And if the deformation breaks down at some point beta, then we need to construct a destabilizing test configuration. So that involves three things. That's x0 is a limit object. There's a one parameter subgroup that degenerate x to x0, and then show the Fataki invariant is non-positive. So it is at this point. So this construction of x0 is a key issue. So and this is where we use metrics to see this x0. So the point is that we can, as beta I tends to beta, we can just view this as metric spaces. We forget about the complex structure, forget about the Kähler-Einstein equation. As a metric space, they can take a so-called Gromov-Hausdorff limit. So this is the metric space, compact, and we want to recover the complex structure on this space, and that will give us x0. So this needs to bridge with algebraic geometry, and this is the reason is because metrics determine complex structure. But we need to understand the metric good enough to recover the complex structure. So in a related context, so for Kähler-Einstein matrix on Fano manifolds without the cone singularities, say a sequence yi omega I is just smooth Kähler-Einstein matrix. The study of limit space fits into the remaining convergence theory developed by Chigo-Cody in the 1990s. So this is joint work with Donaldson. So in this context, we proved the algebraicity of Gromov-Hausdorff convergence. So the Gromov-Hausdorff limit space is naturally a Q-Fano variety. So it's a Fano manifold with mild singularities. The convergence can be realized in a flat family over Hilbert scheme, Y infinity of the means Kähler-Einstein metric in a suitable sense. So the upshot is that this Q-Fano variety is an algebraic variety. So everything is algebraic. The singularity is also algebraic. So for us to construct this x0, it requires an extension to the case with cone singularities. There are new technical difficulties has been to do with the Coleman-2 singularities. Especially this Coleman-2 singularity, they can merge. If you just play with a flat cone matrix in dimension 2, you can see it's an exercise to see that you can possibly merge singularity together when the cone angle is bigger than pi. It also involves PDE theory for this complex Monod-Ampere equation with singularities. So technically there are many issues. Anyway, let's skip part of the slides. So there are many other proofs of the Kähler-Einstein results. There's proved by data regularity using the classical continuity paths. That's a joint work with Chen and Wang using rich flow based on their resolution of the Hamilton-Tian conjecture. And that's a variational approach due to Berman, Bookson, Johnson. This proves the result under the slightly stronger assumption of uniform case stability. This is more along the formal picture. So there are extensions and further developments. So this is a joint work with Cristiano Spotti and Chen Jianyao. So we prove that a K-stable smoothable Q Fano variety admits a Kahler-Einstein metric. So this is a singular variety. You can still talk about K-stability. You can also talk about Kahler-Einstein metric. So the interest of motivation is that this is related to compactifying the modular space of K-stable Fano manifolds. So if you compare, you will not necessarily meet these smoothable varieties. And so that actually was used by Li, Wang, Xu, and Odaka to construct the moduli space. And then there are also explicit descriptions of the moduli spaces in some cases. As general, for general Q-Fano varieties, not necessarily smoothable, Li proved that the uniform K-stability implies existence of the weak Kahler-Einstein potential. So there's there's a difference between Kahler-Einstein potential and the Kahler-Einstein metric. So on the smooth case, when we only talk about this potential function being smooth, so of course it's always defining a metric. But when on a singular variety, you can make sense of this equation in the sense of pluripotential theory. So the potential function is only continuous, and so it's not clear in general that what's the behavior of this metric near the singularity. So I think that there are recent progress along this line following the PD estimates of Guo Feng Tong. So as I mentioned, the algebro-geometric study of K-stability has seen major advances through the work of many people. In particular, so recently the Liu, Xu Zhang, they proved that the K-stability of a Q-Fano variety implies uniform K-stability. So together with because uniform K-stability will imply the existence of a Kahler-Einstein potential by Li's result. So and the moduli space for general K-stable Q-Fano varieties were constructed algebraically by Xu and his collaborators, and so in the algebraic work, there's an alternative to the Chiga coding convergence by the deep work of Burka. And then there's a general CSK setting. There's a formal picture is now made precise. So I think I will skip this. So in particular, there's a result of Chen and Chen that shows that essentially there's an analytical criterion for the existence in terms of geodesic stability, and there are works relating this to stronger notions of K-stability. So I want to spend the next 7 minutes or so to talk about some other aspects of this philosophy, that natural objects from canonical Kahler metrics should have algebro-geometric meaning. So the existence of Kahler-Einstein metric, existence of canonical metric is related to K-stability, but then you can just by playing with this metrics, you will generate many different questions in the algebra geometers can study, and yeah, so there are lists of this. So local stability theory. So this is about the algebraic singularity. So we consider the Gromov-Hausdorff limit of Kahler-Einstein Fano manifold and the singular point. So from a metric point of view, this Chiga coding theory tells that the singularities are conical. So if you rescale the metric around the singularity, you see this metric tangent cones. So of course, in general, it's not necessarily unique from geometric analysis. And the cross section of such cone, if this cone is has smooth cross section, the cross section is Sasaki-Einstein manifold, and this has close connections with physics, ADS-CFT correspondence. In particular, there's a work of Martelli, Sparks, Yao about the volume minimization for Sasaki-Einstein matrix, and then they proved this surprising result that the volume of a Sasaki-Einstein manifold is an algebraic number. And there's also a generation of this Yale's conjecture to the Sasaki-Einstein matrix by Collins-Zagalidi. So using this, actually, crucially depending on this algebraicity of the volume, so Donaldson and I proved that there is a unique metric tangent cone, and this has a algebro-geometric description. So this is something you know that there's a metric tangent cone, but can you describe in terms of algebraic rescaling of the equations? So, of course, you naively you expect that you just do some like weighted tangent cone in the algebraic sense, but unfortunately, this is not the case. You need two steps in general. So it's so we call it two-step degeneration theory. So there is a valuation on the local ring and the P that sends the singularity. It's just algebraic dilation to something which is a cone. It's called the algebraic Fano cone. But this W is not necessarily equal to CP in general. So there's a further equivariant generated from W to CP that's required. And so you should compare this with, for bundle theory, there's a Hadamard-Simon filtration and the Shadri filtration that degenerates a bundle to semi-stable bundles and to polystable bundles. So the CP is a k-stable object, and in this W, you don't see from the metric directly. You have to do this procedure. It's a purely algebro-geometric object. It's only semi-stable. And we proved, we conjectured that these are actually, so we construct W and the CP using the metric, but then we conjecture that's all depend on metric, so they are algebro-geometric invariants. And then Chile reformulated this conjecture, it make crucial observation using a generalized volume minimization principle, and this conjecture has been studied by many people and proved and generalized. And then the next is optimal degeneration theory. So if a manifold is not stable, then there's no Kahler-Einstein metric. But then what can you say about it? You can run Ricci flow on this. So it's well known that the Ricci flow will, if you normalize this way, it will exist for all time, and then it actually degenerates. So we proved so using the Chen result. We actually it's a similar thing. It's a two-step degeneration to something which is Ricci soliton. And we conjecture that this is also algebraic, and this also proved by many people. So that's just a similar analog to the local setting. And then one can also study stability at infinity. So you can consider a complete Calabi-Yau matrix, a non-compact Calabi-Yau matrix with Euclidean volume growth. We call this AC, asymptotically conical Calabi-Yau matrix. So this is dual to the local setting. You can scale down the metric and you get asymptotic cones. So that's not surprisingly, there's also a simple two-step degeneration theory for the asymptotic cone. But the surprising thing that for us is that the difference is that you only need one step. So the W is always the same as C. We prove this under the assumption that the curvature decays quadratically fast, and we conjecture this is true in general. So this is quite different from the local setting. So in general, this is related to Yale's compactification conjecture that its AC Calabi-Yau manifold should be quasi-projective, but this still remains to be studied. And for non-compact manifolds, the difficulty is that there's no uniqueness. So even on C3, you can find different Calabi-Yau metrics with Euclidean volume growth. So it's not so even to talk about uniqueness, you have to play the different game. So I suggest there's a way of studying this. You don't just consider the manifold, you consider manifold together with a degeneration, algebraic degeneration to a k-stable Fano cone. So there are some conjectures in our paper about this. So lastly, it's a bubbling theory. So look, I talk about the local singularity. You start with singular space itself. You can look at singularity. You can dilate. But if you want to understand singularity formation from a sequence of smooth metrics, forming a singularity. Then to study the dynamic picture, one has to do the scaling before you take limit. So you have xj, omega j converging to a limit. You have to dilate for each j, choosing a lambda j, and then take a limit. So this we call them bubbles. So look at this picture. So on the left, you can imagine the sequence of objects where this pj around pj, this small part converging to p, all the topology disappear. So if you just look at the limit space p, you don't see this topology. But instead, if you just rescale so that this topology survive, then this rest part of the space will be pushed to infinity. So you get on the right, you get a non-compact space. So iterating this procedure, you can further rescale, and then you get a bubble tree. So I proved that the bubble tree terminates in finitely many steps. So so if you just scale a little bit, you get the tangent cone. But you scale a little further, you will get a space which is non-compact, and this asymptotic cone agrees with the tangent cone CP. So that's called a minimal bubble. So this question is the algebraic meaning of this bubble tree. So so if we start with a flat degeneration of KLT singularities with a section, this section plays the role of the base point. Can we define algebro-geometrically some new space that can only that will give rise to this minimal bubble? Because this bubbling that I talk about depends on the metric. You have to have the metric to take limit. But because there's this belief, this is a natural objects from this canonic metric, one should have an algebro-geometric meaning of this. So you just take an algebraic degeneration, there should be a way of constructing this. So there are some recent work about Dhaka on this and related questions. So this is the case when I talk about as a non-collapsing. So with a space, even they form singularities, the dimension does not drop. There are actually more interesting questions coming in the collapsing setting, but I don't have time to talk about that. So let's finish here. Thank you.
Is there any question or comments?
Yes, in 2 dimensions, it's easy to construct for the moduli space for degeneration. Yeah, so in 2 dimensions, the point is that yeah, in 2 dimensions, so if you have xj, these are Einstein, let's say, Kahler-Einstein matrix, complex dimension 2, and non-collapsing, then you know that the limit will always be orbifold. And then there's a bubble tree. The bubble tree is always consists of the ALE orbifolds, orbifolds. And these are actually all classified by Kronheimer. So if you this is abstract, but if you look at the explicit algebraic families, actually you can see them.
Any more question? I have a simple question. So for instance, on Cn, it's possible to formulate some algebraic or topological conditions that the Kahler-Einstein metric is unique under some assumptions.
Yeah. So no, that's a good question. In C2 is if it has Euclidean volume growth, it's known to be unique. So essentially due to topological reason, because there's no cycles in the non-trivial cycles in the space. in high dimensions, if you just add a topological, you have to add conditions at infinity. So my point is that the uniqueness should not be asked just on C3, but you together with some. I mean, you can think of this as together with some compactification of the C3, or you can think of this C3 together with. So C3 as a complex manifold is very complicated. It's automorphism group is infinite dimension, but you should you think of C3 as a deformation of some cone. So, and this cone is, when this cone is prescribed, then such matrix on C3 with this prescribed cone, this space is correspond to Calabi-Yau matrix on this cone, and that's unique. So, so we have some discussion, but I think I believe this is the correct formulation of the problem.
Okay, so if there is no more questions, let's thank our speaker again.
Thank you.